Today we're going to be representing functions in different forms. Now we're going to do several slides that have this exact same format. You'll have an equation, you'll have a graph, you'll have a table, you'll state it verbally, and you'll have a relation. So this particular graph, we are starting with an equation. Now, anytime you're given an equation, I highly recommend you make a table. I call this particular table a T-chart. Notice I started with a T and I put in my XY. Now, we know that the input values are our X values. So I can pick whatever X values I want to figure out what the possible Y values would be so that I can graph this. When we're thinking about picking out X values, we want X values to the left of the Y-axis and to the right of the Y-axis so that we have a good indication of what's happening on the left side of the Y-axis and the right side of the Y-axis. To limit ourselves to just one side is going to really restrict and limit your understanding of the graph. So, that being said, it would be helpful to have some values like -1, -2. It would be helpful to have some values like 1 and 2. And most importantly, we really want to know what's happening when X is 0. So we'll list those ordered pairs: -2, -1, 0, 1, and 2. So at this point, all we really need to do is plug those X values into this equation. So 3x minus 4. We're going to substitute in each X value. 3 times -2 minus 4. Well, 3 times -2, that's -6, minus 4 is -10. We go on to the next ordered pair. 3 times -1 minus 4. 3 times -1, that's -3, minus 4, that's -7. Go on to the next ordered pair. 3 times 0 minus 4. Well, 3 times 0 is 3 minus 4, 0 minus 4 is -4. Go on to the next ordered pair. 3 times 1 minus 4. 3 times 1 is 3, minus 4 is -1. Go on to the next ordered pair. 3 times 2 minus 4. 3 times 2 is 6, minus 4 is 2. And now we can graph these ordered pairs. So we come back to down 10. That's going to be somewhere way down here. We're not going to graph it. We come back 1, down 7. While it still extends off of our graph, we know what even increments are going to be, so we can put it down there just to get an indication of where it'll be. We graph 0, -4. We graph 1, -1. We graph 2, 2. Those are our ordered pairs for this particular function. Now, certainly any ordered pair on that line is a valid solution, but we just picked these inputs so we could get outputs to help us graph. Connect the dots, and we have a straight line that goes through these ordered pairs that represents this function. Now, how would we state this verbally? We would say y. Let's do that again. Y is equal to 3 times a number minus 4. All right, and then how would we state it as a relation? We know that a relation is a set of ordered pairs. So we need several sets of ordered pairs that represent this function, that represent this graph, that are consistent with our verbal. Well, where are we going to get several ordered pairs? Our T-chart already has them, so we just need to list them. -2, -10. -1, -7. 0, -4. 1, -1, and 2, 2. And we've finished one problem. All right, our next example. This time we're starting with a graph. The nice thing about a graph is it also identifies several ordered pairs. Not as many as our table did, but we could certainly fill in our table knowing that we have some x and y values. We're going to go ahead and put 0 in the middle because we can see that this graph is clearly going through 0, 0. We'll put -1 because we can clearly see that at -1 it has a y value of 4. And we'll put 1 because we can clearly see that at 1 it has a y value of -4. All right. Now, this is a graph where recognizing that our graph has direct variation comes into play very well. Remember that with direct variation, k is equal to y over x. And since this is a straight line that goes through the origin and it does have direct variation, we just need to know the value of k, and we find that by taking any y and putting it over its x. And notice I just gave you a bunch of y's and x's. The only one you cannot use with direct variation is the origin 0, 0. Otherwise, I can take any x or any y and put it over its x. So let's take our positive one. We have a -4y over a positive 1. -4 over positive 1 is equal to -4. So we have determined that the k value is equal to -4. Well, our graphic equation for a direct variation line, we've talked about several times as being y equals kx. And this is a standard you would have covered last year in 6-7. And we just identified the value of k. The value of k we said was 4, so our equation will be y equals -4x. All right. Well, that's a useful equation to have because we really want 5 ordered pairs here. So let's go ahead and find -2 and 2. Using the equation y equals -4x, we'll plug in a -2. So -4 times -2. Negative times a negative is positive. 4 times 2 is 8. All right, let's plug in the next ordered pair, 2. So -4 times 2. Now that gives me -8. One of the things that's beneficial to notice with direct variation is the opposites that are happening across the origin. So if I find ordered pairs in one direction, I know the ordered pairs in the opposite direction are going to have the opposite value. Verbal statement. All right, we can say that y is equal to -4 times a number. That's a simple statement, but it represents our function. All right, as a relation, all of these ordered pairs that we just wrote down, they become our relation. And we move on to the next slide. All right. Well, this time I was given a table. Interesting. So we have -2, -2. Come back 2, down 2. We have 0, 0. We have 1, 1. We have 3, 3. All right. We've now made a line. We again have an equation that goes through the origin, so k is equal to y over x. And we just need any y value and its x value. So that's going to be equal to 1 over 1, which simplifies to 1. The value of k is equal to 1. So our equation is going to be y equals 1x Or you can simply say y equals x. Because we know that there's an invisible, unseen 1 sitting in front of that x. All right, verbally, y is equal to a number. Now, another way I've heard these stated is you can say a number is equal to another number, and I'd be fine with that as well. All right, we're down to the relation. The table gave us 4 values. We're going to use those 4 values. -2, -2, 0, 0, 1, 1, and 3, 3. We've got our relation. All right. Wait a minute. What in the world is that? X squared? Well, that seems a little funny. But that's okay. We're going to follow the same process and see what happens. Again, x and y. I want to see what's going to happen that side. I want to see what's going to happen on that side. So we're going to plug in our numbers, -2, -1, 0, 1, and 2. All of those values will go into the function given. So x squared minus 3. So let's plug in our first term. -2 squared minus 3. Well, -2 times -2, that is 4. Minus 3, that's 1. -1 squared minus 3. -1 squared, that's 1. Minus 3 is -2. All right, let's plug in a 0. 0 squared minus 3. 0 squared is 0. Minus 3 is -3. All right, let's plug in a 1 squared. 1 squared is 1. Minus 3 is -2. And lastly, let's plug in a 2 squared. 2 squared is 4 minus 3. That would be 1. Now, what kind of pattern are we seeing with this particular model? Yeah, we have opposites in our x's, but notice our values pivot around the value -3. Let's see what this looks like when we graph it. So we have a -2 up 1. We have a -1, -2. We have a 0, -3. We have a 1, -2. And we have a 2, 1. That's an interesting looking graph. First, we should realize that it is not linear. Definitely not. It's still a function. It passes our vertical line test. There are no x's that are going to the same y values. Sorry, no x's that are going to different y values. Each x is going to its own individual y value. All right, how would we state this verbally? We would say that y is equal to a number squared minus 3. And then a relation, we've got our ordered pairs from the chart. That part's not changing. -2, 1, -1, -2, 0, -3, 1, -2, and 2, 1. All right, next example. F of x is equal to -1 fourth, f of x is equal to -1 fourth times x plus 3. So we have f of x equal to -1 fourth times x plus 3. That wasn't too bad. Well, we'll take that. We'll make a table. X, Y, -2, -1, 0, 1, and 2. Hopefully you're getting in the pattern of putting those numbers down. But, Mr. Gable, that looks bad. -1/4 x plus 3. -1/4 times -2 plus 3. Well, -1 times 2, that's positive. That's going to give me 2/4, which is 1/2 plus 3. So now I have to make that a common denominator. So 1/2 plus 6/2 equals 7/2. That seems a little messy. Surely there's got to be an easier way. Well, there is an easier way, but the only catch is it deals with slightly larger numbers. So you get to decide if you're going to like the easier way or if you want to stay and live with fraction world. The easier way is to look at the denominator and pick multiples of the denominator. So we're always going to start with 0. Our first multiple of 4, 4 times 1 is 4, 4 times 2 is 8. So we're going to start with -8, -4, +4, +8. Okay, let's see why. -1/4 times -8 plus 3. Negative times a negative gives us a positive, which ends up with 8/4 plus 3. Well, what is 8/4? 2 plus 3, which equals 5. So when we plug in a -8, we get a +5 for our y value. So we're dealing with all whole numbers. At this point, you should be able to do some of these in your head. So -1/4 times -4 plus 3. Well, -1/4 times its reciprocal. It's going to make it +1. Plus 3 is 4. -1/4 times 0 plus 3. Anything times 0 is 0. Plus 3 is 3. All right, -1/4 times 4 plus 3. -1/4 times 4, that's going to give me a -1. Plus 3 is 2. Now, hopefully you see a pattern happening here. As my x's are increasing, my y's are decreasing by 1. So we can already go ahead and tell. If I plug in an 8, I'm going to get a 1 for my y. Let's graph. -4, up 4, 0, 3, over 4, up 2. Well, that definitely appears to be a linear pattern. Oh, come on. So we have a line. Now is a relation. You've got all your ordered pairs from the table. -8, 5. -4, 4. 0, 3. 4, 2. And 8, 1. All right, next problem. You're given the relation. See if you can work this one backwards to figure out the rest of the boxes. And I'm going to give you just a minute or two to see if you can do this one on your own. All right, let's check your answer as we go. All right, I can make a t-chart using these values, but before I do, let's plug these values into the graph and see what we get. Over 3, up 6, that's going to be way up here. Over 5, up 10, that comes way off my graph. Over 1, up 2. Okay. So it appears that to get from one ordered pair to the next, I come down 1, 2, 3, 4 units. I come over 1, 2. So I'm going to come down 1, 2, 3, 4 more units and come down 1, 2 so that I keep the constant rate of change. I'm going to come down 1, 2, 3, 4 units over 1, 2. Now, if I'm coming down 4 over 2, what's another way that we could say that? I'm coming down 2 per 1. Well, does that work? Let's check. Start at our top right. We'll come down 2, back 1. 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 That sure does work. Now, I probably should have been a little bit more consistent with the fact that this is a positive slope graph and gone from left to right. Bad habits sometimes are hard to get rid of. So let's look at that a little bit differently. We started here and worked up 4 over 2. And since I went up 4 over 2, working left to right, my slope is 2. 2 is a positive number, gives me a positive slope. So now we can connect the dots. And this is where I would grab my information from for the t-chart. So we have x, y, -2, -1, 0, 1, and 2. I don't really have to plug anything into an equation because the ordered pairs are on the graph. -2 down 4. -1 down 2. 0, 0, that's in the origin. Over 1 up 2. Over 2 up 4. Now we have a direct variation graph. So y equals kx, where k is representing my constant rate of change, my slope. So our equation, y equals 2x. Verbally, y is equal to a number times 2. Now, lots of different ways to say this. You could say y is equal to double a number. You've got some options there. All right, here's another one. Let's see if you can give this a try. I'm going to give you about 1 minute head start. Obviously, if you're watching the video at home, you can fast forward through or pause for as long as you need to. All right, if you need more time, you can pause the video. We'll start with our table, x and y. Now, for this particular table, I'm going to find perfect intersections. So notice it intersects perfectly there. It intersects perfectly there. Intersects at the origin. Appears to intersect perfectly there and there. So that gives me 5 ordered pairs. Well, these 5 ordered pairs, let's see what they are. 0, 0, over 1, 2, 3, 4, 5, up 2. Over 1, 2, 3, 4, 5 more, so that's 10, up 2. All right, we went back 5, down 2. And we went back 5 more, down 2 more. Well, the first thing I recognize is that this graph has direct variation. It's a straight line and it goes through the origin, which means it's going to use the y equals kx version of our graph, or of our equation, and our k is going to be equal to y over x anytime we have constant of proportionality or direct variation. Which means I just need to know any y and any x. I may as well pick this one here because those are already simplified numbers. So y is equal to 2, x is equal to 5. My value of k then is equal to 2/5. Now, how did I know we were going to have a 2/5 value of k? I knew we were going to have a 2/5 value of k because when I moved over 1, my line was not even above the first increment. It was a fraction. It really is sitting at 1/2. It's just hard for us to tell that that's 2/5. So we look for whole value increments on our graphs. So y equals 2/5. X is our equation. All right, verbally, y is equal to 2/5 of a number. A relation, again, we've got all these ordered pairs here, so we may as well use them. And we've stated our relation. All right. Again, give this one a try. All right, let's see what we got. F of x equals x raised to the power of 4. Well, that's an interesting looking graph. Let's see what that does. So we have our xy table where we're going to plug in our -2, -1, 0, 1, and 2. Okay. So let's start with x. Oops, sorry. -2, my value of x, raised to the 4th power. That's the same as -2 times -2 times -2 times -2. I have 4 negatives getting multiplied. That's going to give me a positive number. 2 times 2 is 4, times 2 is 8, times 2 is 16. All right. -1 to the 4th power. Well, we've already identified the pattern, so we're going to have -1 multiplied 4 times. That's going to give me 1. All right. 0 to the 4th power. That'll give me a 0. 1 to the 4th power. That's also going to give me a 1. And 2 to the 4th power. Well, that's the same as our -2 to the 4th power. So that's going to get me 16. So we have negative 2 up 16. That's really far up. Negative 1 up 1. I'm not going to graph the negative 2, 16, but I'm going to notice that my graph is going to be coming from somewhere right here because it's got to hit 16 as the next ordered pair for a y value, and it's going to have to be going really steep to get there. 0, 0, 1, 1, and then over 2 up 16. So again, we're coming pretty steep. Now, there's a little bit more going on in this graph than what you're going to be able to see from these ordered pairs, but that's okay. We're not ready for x to the 4th power. But I wanted to show you that you can graph any equation roughly by using a table with x and y values. So this graph is going to come down, do something funny here. Oh, sorry. Come. And then come back up. All right. As a relation, we got negative 2, 16. We got negative 1, 1. We have 0, 0. We have 1, 1. And we have 2, 16.